Hello, welcome to our webinar, Powering the Future Innovative Energy Harvesting Solutions for Wireless Sensors. I am Kevin Zamzo, Director of Product for Grace Technologies. Over the years, I have experienced issues with battery life that have led to more frequent replacement than desired or even abandonment of beneficial sensing due to limited battery life. This webinar will highlight the need for alternatives to batteries and share some innovative energy harvesting options. We will focus on thermal energy harvesting and share some case studies at the end. During the presentation, please feel free to enter questions about the webinar content in the chat, and we will address some of them at the conclusion of the webinar. According to this study by IoT Analytics, there are already around 15 billion connected IoT devices. This number is expected to double to about 30 billion devices in the next 4 years or so. Most IoT devices are wireless, from short-range Bluetooth or Zigbee in the dark gray of the chart, to Wi-Fi in the light gray and cellular in multiple areas, dark and light red and light blue. Longer range private wireless systems like LoRaWAN are shown in the dark blue. That's commonly used in industrial sensing. The difficulty of running a wire that drives the use of wireless sensors also typically means a battery-powered wireless sensor. Unfortunately, batteries have a limited life. The vast number of battery-powered IoT sensors creates a waste battery problem. While some of the batteries will be recycled, many will end up in landfills and leach toxic, corrosive chemicals into the soil and groundwater. There is a trend towards wireless sensors that do not allow replacement of batteries. The thought is a 10-year battery life is about the same as the sensor life. This is true provided that the environmental conditions are optimum and the sensor update rate is at the normal published spec. But in cold or hot conditions, the battery life will be much shorter and exacerbates the waste problem through sensor disposal. Disposing of so many batteries is at odds with many companies' sustainable development goals. But even if that is not a driver, perhaps economics are important. Beyond the environmental costs of disposing of tens of millions of batteries, there are substantial economic costs. Using some conservative numbers for battery life, labor costs, and battery sensor costs, note that in industrial applications, batteries tend to be more expensive, either custom battery packs or lithium thionyl chloride type of chemistry. So the costs are a little higher. Note that also that the time to change a battery includes the time to identify and locate, paperwork and logistics, travel to and from the site, actually changing of the battery or sensor, verifying operation after replacement, and disposal of the battery or the sensor. Even with the 1 hour rate, we assume that multiple batteries changes can be done in one trip. With all this, with just 50 million battery powered IoT sensors, that's 6,000 full-time people just changing battery and sensors, which is hard to imagine, particularly in tough environments or hazardous locations. Fortunately, there are options to perpetually power many of these wireless IoT sensors. There is energy all around us that can be scavenged to power wireless IoT sensors. We are familiar with solar energy harvesting as a renewable source to power the grid and our homes, and you even see these on electric vehicle chargers that are around now. Less familiar are kinetic energy harvesting, but perhaps you have had an automatic watch that winds the mainspring through wrist movement. Vibration is also a common kinetic energy source. Harnessing electromagnetic energy, such as radio waves, has recently moved from the research labs into commercial solutions. And lastly, a significant amount of heat generated by equipment and processes is often wasted, but can be harvested to power IoT sensors. Next, we will briefly look at each of these ambient energy sources, including some of the pros and cons of them. For mechanical energy harvesting, piezoelectric generation is perhaps the most common method. An example mechanism is the internal energy harvesting cantilever beam in the upper right of the slide. Strain induced by movement is converted to electrical energy by piezoelectric transduction. Some piezo materials include single crystals, ceramics, and polymers. While piezoelectric generators have many benefits, a major constraint is the limited frequency range for efficient energy conversion. As you can see in the graph in the lower right of the slide, there's a steep drop-off away from the optimum resonance frequency in the efficiency of the piezoelectric generator. Harvesting energy from light has been used extensively outdoors. In industry, solar power systems have been used to power remote terminal units and IoT gateways and other devices for many years. There is also ambient light indoors. Sadly, I'm old enough to remember the advent of light-powered calculators. While a large solar panel can provide many amp hours of 12 or 24 volt DC powers, the panels can be large in northern latitudes where insolation, which is the amount of light energy per square meter over a year, is low. Only in a few places for a limited time does the sun shine for 24 hours per day, so battery backup is necessary in these solar power systems. This complicates the system, and in addition to maintenance of the panels, which can get soiled by dirt and bird droppings, need to be cleaned, the batteries themselves would need to be maintained. Perhaps least known is the harvesting of wireless or radio frequency energy to power sensor nodes. Sensor nodes harvest RF energy from nearby powered radios transmitted signals. Some commercial systems now have been introduced in the market after academic research was performed in the last 10 to 20 years. An example was the University of Washington had a power over Wi-Fi research program. A major limitation is the significant attenuation of the transmitted signal with distance, which is known as Free's law or free space path loss. For example, the signal is reduced by a factor of 10,000 only 1 meter away from the transmitting antenna, and is reduced by a factor of 10 for every additional 10 meters. Also, the transmit duty cycle needs to be quite high if we're going to provide enough power, and wireless IoT type sensors typically are not transmitting full time. Examples, there are, however, commercial solutions that have been innovative in overcoming these limitations and optimizing the RF energy harvesting. And examples include both EPs, which is pictured, a diagram of their solution is pictured to the left at the bottom, and Onio's Zero microcontroller. The last of the four types we'll explore today is thermal energy harvesting. Focusing on thermoelectric generation, but other methods include pyroelectric, where voltage is produced by certain materials when heated, typically semiconductors like gallium nitrate. Thermomagnetic, where the heat impact on magnetism using ferromagnetics like gadolinium solenoids wound with copper wire, or thermoelastics with shape memory alloys are other options, but commercially, we'll most often see thermoelectric generators. In a thermoelectric generator, or I'll refer to as a TEG, T-E-G, a thermal gradient between N and P-type materials, such as in a bismuth telluride, produces electricity. The larger the gradient, the more electricity that is produced. Thermal energy is pervasive in industrial environments. If a surface is warm to the touch, it is generally suitable for thermal energy generation. There are many examples in industrial settings, from rotating equipment like pumps, motors, and compressors to warm pipes and process vessels. Note that it's very possible to run a power cable from the thermal energy generator to an IoT sensor if the heat source is a number of meters away from the sensor. In a thermal energy harvesting system, there are a number of key components, which may be integrated into a single housing with the sensor, or maybe a separate thermal energy generator, and could have even separate energy management systems. But the key components are the thermal energy generator itself, which will often include some sort of method to radiate excess heat on the cold side of it. There's an energy management system, which could be an integrated circuit that's used to regulate voltage to the sensor and also provide energy to a storage mechanism like a super cap so that peak wireless sensor power requirements can be met. Energy storage could also be a rechargeable battery. TEGs will have different power curves depending on factors including materials, size, and design efficiency. This is an example curve for a thermoelectric generator suitable to power a wireless pressure, temperature, or level transmitter that is normally powered by 2 lithium thionyl chloride batteries at 7.2 volts DC. The ambient temperature is 25 degrees centigrade in this curve, and it illustrates the power output from thermal gradients ranging from 10 to 70 C. Note the increase in power when airflow is removing heat from the cold side of the TEG. At the higher thermal gradients, multiple transmitters may be powered. Next, we will share an example of a commercially available thermal energy harvesting system for wireless sensors. This system is the Perpetua Power Puck. I have one here in my hand. You can see they're fairly small and can be magnetically mounted as well as mounted using pipe standoffs. The TEG here is separate from the energy management and storage system, which is either a module that can be replace the battery module inside a wireless transmitter, or it can be from a separate unit that is wireless sensor independent. Power options support typical battery configurations from 3.6 to 12 volts DC. This solution may be used in hazardous locations if allowed in combination with the transmitter. Next, some applications will be shared that illustrate the value of thermal energy harvesting for wireless sensors. Wireless sensors are often used in difficult to reach, sometimes moving applications, so access to change batteries can also be difficult. In process plants, fast process variable update rates are needed for open or even closed loop control. Rates can be as fast as 1 to 4 seconds. So another benefit is saving time to put on personal protective equipment when going into hazardous areas and to reduce exposure inside those hazardous locations. Upstream oil and gas pads are often unmanned, so eliminating a maintenance operation to replace batteries saves time. We are often asked if multiple wireless sensors can be powered from a single power puck TEG. The answer is yes, provided there is enough of a thermal gradient from the heat source to the ambient temperature. In this example, steam is used to inject into the ground to recover oil, and there's a very large thermal gradient. So in this example, there are 3 transmitters that are powered from a single power puck. Warm reactor vessels or holding tanks are another excellent heat source for thermal energy harvesting. The desire to publish process variable data quickly is a common theme and results in frequent battery changes without energy harvesting. Batteries do not like very cold conditions, and as we're often reminded of when our vehicles struggle to start during frigid winters in northern latitudes. Solar is also not a good option with only a few hours of sun in the winter. If a heat source is available, thermal energy harvesting enables desired monitoring without the cost of running long-distance wires. Many factories have drives, compressors, and other warm surfaces that can be used to power remote machine health monitoring applications. Vibration monitoring is a good example, with balance of plant rotating devices often not monitored due to the cost of providing power and communications. You can see the example here where the vibration sensor is attached to a motor and we're able to get enough heat using that separate power management unit. So please watch there's a poll to let us know if you'd like more information or wish to share specific application needs. Now we will check the chat for questions. So the poll is active and we're starting to see some responses there. If you have questions, feel free to add them to the chat. So there's a question about how long has this product been out? This has been in the market for quite a few years with thousands of installations. And the only issues that have been seen is one or two units have been returned that have looked like they've been in a fire. So it's very reliable. There's no moving parts to wear out. So typically a 20+ year lifetime is expected. So there's another good question about how do you determine what level of power will be generated? So that'll be specific to the energy harvesting mechanism. So what you would look for is most of the manufacturers should have curves that will indicate the amount of power generated based on whatever energy is being harvested, or in this case, a thermal gradient. So, and we have different voltages so that it's typically, for example, about 12 milliwatts with a 30 degrees C thermal gradient at 7.2 volts. And more or less depending on airflow to help manage the thermal gradient on the cool side. Dust on the puck is a good question. So if there's dust on the puck, it would just impact the cooling of the fins. It's actually designed to to not capture that as readily if you saw the splayed design of the puck. So the main issue is it'd be the same as if there weren't airflow. It would be less cooling there to maintain the gradient. So there's no maintenance required for these. So there's no moving parts. It's two dissimilar two metals that are generating current based on the thermal gradient. Yes, copies of the presentation will definitely be made available. There's a recording of this that you can watch or share with colleagues who weren't able to make the presentation. Classification area, there's a question on what classification area these are rated for. They're rated for class 1, 2, and 3 division 1. So the highest, the most hazardous location rating for gas, dust, and fibers. Also ATEX and IECX zone 0 applications. Good question. And that was specified on one of the slides. So cost per puck, cost per setup will depend on the number of sensors that are being powered. What we find is typically the cost is equivalent to 1 or 2 battery changes, and you will start to have a return on investment, with the installation. They're very easy to install and retrofit into the field. So very good questions. Very much appreciate the questions that are being asked. If you have more questions, feel free to reach out, poll or contact Grace Technologies, and we'd be happy to discuss your specific application needs. So there's a question here that states that I'm guessing that the return on investment depends on how often you are sampling the data, 1 second versus 30 minutes. It's correct. But even it also depends on the environment. So 1 second will consume the battery, quick in a typical environment. But if you get into a colder area where the ambient temperature might be -20, -30, even colder, like in the tar sands, the North Slope, or even in the Bakkens in the U.S., these different oil locations, you're even with a slower update rate, your battery life will not be as long, and you will also not have as much power coming from the battery. Good, very good question. Well, if you have more questions, please feel free to reach out. Otherwise, thank you very much for attending the webinar. Well, we got a couple more questions. I'll take those here. If you have a rechargeable battery, would a puck be a source to recharge, or is the puck by itself the solution? So the puck with a consistent thermal energy source, the puck by itself can be the solution. It does have a super cap option to provide additional burst power as needed. We refer to it sometimes as a belt and suspenders approach. The battery could be helpful if you have a process unit that has undergone a turnaround and you're going through startup and you don't have the heat, so the thermal gradient isn't present at the heat source. Considerations made for outdoor applications when selecting between solar and thermal energy harvesting. The number one consideration you would typically look at is your latitude, and based on the latitude, there's charts that you can see what your insolation factor is, and that will give you some idea for the sizing of the solar panel required to power your devices. So that would be one. The cost will increase as the size increases. So that would, there's a little more complexity as well. So if you have a good thermal energy source that's consistently providing a thermal gradient, that's going to be more reliable and not require the battery backup that the solar requires. I actually don't know how large the horsepower is in the motor in the diagram. It's more about the heat that's generated than the size of the rotating device or the heat source. Very good. Well, thank you very much for attending our webinar. We really appreciate your time and interest, and look forward to hopefully chatting with many of you in the future.